Hi, I'm Emma Turner. I'm a software developer here at Trilotech. I work on the core team, so protocol adjacent stuff. Specifically, sort of in the 13, 14 months that I've been here at Trilotech, I've mainly been on the rollups team, working on scaling Tezos with our recently released Smart Rollups that went live in the Mumbai upgrade a few weeks ago. While I've been at Trilotech, I've primarily been working on the rollups team. We've been working with developers at Nomadic Labs, Marigold, and Functory on bringing smart rollups to Tezos. I guess the start of rollups is sort of why do we need them? I think most people who are sort of involved at all in blockchain doesn't have to be Tezos, probably Ethereum or many others. There's a lot of conversation about rollups and the need to scale ultimately, because this is what it's about. And in normal sort of blockchain operations, nobody trusts each other. It's a decentralized network, so there's no real coordination beyond just the protocol, and that means that every single participant in the network has to verify and validate what anybody else does to make sure that everybody is not only saying that they play by the same rules, but are actually doing so. This causes some issues with throughput, because any computation, be that a transfer or a smart contract call, or potentially other operations depending on the network, must be run by every single node in the network, or sufficiently many nodes to reach consensus. In Tezos' case, we actually pride ourselves on having relatively low hardware requirements. We don't want there to be a big barrier to entry, because otherwise you sort of price people out, and your decentralization suffers as a result. So on Tezos, we want people to be able to run nodes just on Raspberry Pis, for example. They're not super powerful machines. They are fairly good, and they've improved a lot, but at the end of the day, they're not some 64 core Threadripper or whatever the latest hardware is these days. So if we want to scale, we need to find a way to sort of do more computation through the network, but we don't want to increase the hardware requirements on the network, because that means that the Raspberry Pi will no longer, for example, be able to keep up with everything. So rollups are ultimately a way of rolling up multiple operations into a single operation. That's where the term comes from. And there are various other terms that we'll talk about, but the base idea behind rollups is that you delegate computation off network. It's done by potentially small number of entities who may have more powerful hardware and are therefore able to process a higher number of transactions or operations. And then those operators can report back the state of the rollup, just as a sort of hash of the state of the storage of the rollup back to layer one. So while messages may be going through layer one, just in the base case, ultimately a lot of operations are done elsewhere, and the reporting is relatively light in load on L1. It's just a simple message with a small hash in it. There are then multiple different technologies behind rollups. ZK is one that's often talked about, but the one that we've mainly been working on, and indeed the one that just went live on the Mumbai upgrade a few weeks ago, are smart optimistic rollups. The term smart more or less comes from the fact that on Tezos, when you create a rollup, you give it a entry point type, which is the same sort of thing that you would give a smart contract that you originate on mainnet on layer one. The rollup has a entry point. It's not the only entry point it has, but it has an entry point that kind of looks like a smart contract on layer one, at least two other smart contracts, and that allows smart contracts to directly call and send messages to smart rollups. Um, and then those messages are executed inside the rollup itself. The other term is optimistic. So the there are a few examples of this sort of thing out in the wild on other chains. But optimistic basically comes from, by default, we want to trust that the operators are doing the right thing. On Tezos, anybody can become an operator for a rollup, and that's actually quite a unique thing. Our rollups are a sort of ultimately decentralized layer 1, layer 2 bridge, both from layer 1 to layer 2 and back again, and it's fully decentralized, and there's no multi-sig backing the whole thing. It's baked into the protocol, and so they can do more powerful things. But ultimately, the security guarantees of the computation of the rollup are, if there is one single honest operator for that rollup, then the rollup is secure. So the way that works is everybody reports the state. Everybody who's operating a node in the rollup pays a bond, and they report back the state at regular protocol defined intervals. And if everybody agrees on the root hash, that the hash of the state of the rollup, then everybody is happy, and it continues onwards. And after 2 weeks, a root hash, or a commitment, as we call it, if there's no disagreement at all, or conflict, then after 2 weeks, a commitment can become cemented. At which point that the state of the rollup at that point in time becomes fixed, and certain things become possible, such as any layer 2 to layer 1 messages that were output by the rollup before that commitment became cemented, can now be executed. So that's where the term optimistic sort of comes from. The state progresses forward, and for as long as everybody agrees, then we're happy. But if somebody posts a bad commitment, or there becomes a conflict between two commitments, then a refutation game, or a sort of mechanism between 2 points of a conflict plays out to determine who's right or wrong in that particular instance. And the guarantees that we have are that if an operator is playing, or is progressing the rollup honestly, then any refutation game that they end up playing, they are guaranteed to win. And the refutation game, again, as with everything else with our rollups, is fully decentralized. There is no sort of whitelist of people who are allowed to play or partake in the refutation game, and it just works by dissecting the computation, so chopping up the computation that's happened between two commitments into smaller and smaller pieces, until eventually we get to a small enough piece that we can submit an operation to layer 1 to prove that that small piece of computation must go from this state to this state, at which point the protocol can see, well, I've executed it myself, and it goes to this state, so this state is fine, and the other state is wrong, and their bond gets slashed. On Tezos, the language of choice for writing your rollup programs are WebAssembly programs ultimately. So on sort of well-known examples of particular rollups, say on Ethereum, rollups on Ethereum are often EVM based, so they have the same execution. They have the same ultimate execution model as layer 1 does. That's not the case here. So we went with WebAssembly, which is obviously pretty different to our layer 1 smart contract language, Michelson, for a few different reasons. But ultimately, WebAssembly is a target that more and more languages can compile to. I mean, a lot of programming languages out there can compile to WebAssembly, The question is whether or not they have good support for compiling to WebAssembly, but certainly Rust, C, C++, Go, among others, all have pretty good support for compiling to WebAssembly. And that means that when you create a rollup, you submit the program ultimately that you want to run on the rollup. This program can upgrade itself over time, but you are ultimately submitting a piece of WebAssembly code, and that's what's executed in the rollup itself. So one of the things that I've personally worked on quite a lot at Trilitech is sort of this side of Smart Rollups, what we call the sort of kernels. So ultimately, just the WebAssembly programs that we want to run in the rollup. So that work has sort of partly been spent on writing some example kernels. For example, we have a transaction kernel that is able to receive deposits of tickets, which is a kind of token on Tezos, into the rollup and transfer tickets between accounts on the rollup itself, and then also allows withdrawals of those tickets back to layer one. So it's sort of a couple of thousand lines of code, partly because it's been optimized in a few places. That's just an example, and there are lots of others that we're working on. The other thing that we've been working on as well is we want development of these smart rollup kernels to be as easy as possible for people. There's quite a steep learning curve, or there is certainly a learning curve when starting to write kernels, because ultimately there are a few properties that the kernel developers need to make sure that their kernel adheres to, and there is a particular API in place to be able to interact with the outside world from inside the rollup. So we have a SDK for Rust that allows people writing their kernels in Rust to have a sort of slightly higher level interface and make certain things easier inside the kernel than otherwise would be if you were sort of having to write directly against the API, which is pretty C-like. But yeah, so kernels have a few different jobs. The reason we call them kernels is ultimately when you deposit assets or transfer assets into a kernel, or indeed do operations inside a rollup, you have to trust the kernel. So on layer one, if you call a smart contract, you have to trust that the smart contract does what it says it's going to do. I mean, it's not great if you call a smart contract expecting it to give you something, and instead it takes all your money. That obviously wouldn't be ideal. The same applies to rollups. You have to trust that the rollup is doing what it says. The kernel ultimately is very similar to a kernel that runs on your laptop, the sort of base of your operating system. A lot of the things that you see on your computer are sort of a bit sandboxed by the kernel. They have limited permissions on things. They can't, for example, delete the entire file system, but the kernel can. The kernel can do whatever it decides to do. So ultimately, the kernel is the thing at the center of your laptop or your PC that you trust, or you choose to trust that it is not messing things up ultimately. And similarly, in Smart Rollups, you trust that the kernel won't steal your funds. It won't let other people do operations on your behalf. It will be checking cryptographic signatures and so on, and ultimately behave sensibly as you might expect a kernel to behave, or any contract on layer one. So the kernel has this very important job. Right off the bat is to be sensible, and to not have critical bugs that allow people to steal funds and so on. Now, the way the kernel is executed it is called sort of by the smart rollup effectively, and the kernel has a few different functions that it can perform. The three main things to talk about are the inbox, the outbox, and the durable storage. So the inbox is effectively the collection of messages for the rollup at the given Tezos block that it's executing against. So the key thing to note here is that the inbox for rollups is actually global. So if I send a message to a rollup, not only will that rollup's kernel have access to the message, but every other kernel on every other rollup also has access to that same message. So the kernel has the important job to only look at the messages that it cares about. Now, there are definitely use cases out there where a kernel will want to look at the messages that are being sent to other rollups. You may want to react to that. But on the whole, probably what most people would start off with is you only want to look at the messages that are designated for a particular for the kernel that is actually running. So the messages that the kernel gets are sort of twofold. It gets internal messages and external messages. Internal messages are the smart contract calls that we talked about earlier. Whenever a smart contract calls a Smart Rollups entry point, there's an internal message in the inbox, and this is really key because internal messages have some additional metadata on them injected by the protocol that the kernel can trust, such as where did the call come from, which smart contract was actually calling the smart rollup, and the payload of that message. And the key thing here is the payload for a particular rollup is fixed by the type on that the entry point has. And this is what allows transfers of assets such as tickets to smart rollups and allows that safely. Ultimately, the kernel can take some bytes and parse it into the structure that it's expecting because it knows that the internal message in question is designated for it. It knows what its own type is, and therefore it can say, well, if my type is that of a ticket, and I parse it, and it is indeed, it parses to a ticket, then I know that I now have a ticket, which in a way that's sort of slightly harder to do with sort of smart contract-based tokens. And it unlocks so quite a few uses for tickets, which maybe been missing a bit on Tezos before. So the kernel goes through those internal messages. It may choose to do with them what it likes. The other kind of messages are external messages, and these are just raw bytes. There is a special operation available to users to send bytes directly to the Smart Rollup inbox. The user may add some additional metadata, like the kernel might require might filter external messages by saying, well, if the first 20 bytes of the external message match my own rollup address, then I'll process the message. Otherwise, I won't. So external messages are just directed more or less verbatim into the inbox, and that means that external messages themselves have to contain things like cryptographic signatures to make sure that the operations in them actually come from the users who requested those operations. Unless you have some sort of kernel that only is a global counter. But if you have a kernel that does something useful and actually holds assets, then you probably want to be checking signatures. But this is the beauty of WebAssembly. There's no primitive to say check a certain signature scheme. The kernel just decides. Well, the kernel developer decides whatever cryptographic or whatever signature scheme that they want to go with. And they just pull it in as a library, and the whole thing can pass to WASM. So, it's incredibly flexible, and this is where this is the other side of the term, like smart rollups. Like, ultimately, smart rollups and Tezos, they're not any one rollup. They are a protocol for building rollups, where the really really tricky stuff, the layer 1, layer 2 bridge, is already done for you, and it's decentralized. And you can sort of build on top of it whatever you want. The other two parts of the kernel can deal with are the outbox and the durable storage. So the outbox is kind of like the inbox but in reverse. The outbox allows a kernel to send a message to layer 1, which will then be executed on layer 1 by once a commitment has been cemented. Any user can execute any outbox message. So again, it's fully decentralized. There's no multi-sig or whitelist people allowed to execute outbox messages on layer 1. The downside of this is that you have to wait the refutation period. So by default, you do have to wait the 2 weeks to transfer your assets out if you want to go the fully decentralized route. But there are many options out there to speed this up. For example, you could, as a rollup operator, you could charge people a small fee for any fungible asset. You could say, well, I can see your outbox message and your withdrawal. That's going to come to me. So in the meantime, I will give you funds minus my fee, which is probably a couple of weeks of interest, to give you to unlock your assets directly. You can do it with atomic swaps, but the issue here is it works for fungible assets only. Non-fungible assets you can't really do this with. There may be sort of workarounds, but ultimately you won't have access to your non-fungible token until it actually comes out the rollup and is the withdrawal is executed. But these outbox messages are ultimately just smart contract calls that get executed on layer 1. So they can sort of trigger other smart contracts to do various things. So they are also quite powerful. And then durable storage, the kernel effectively just is given a file system because the kernel has to exit regularly to allow the rollup to do other things, and there's a limited period of computation the kernel is allowed per level. It can run 1,000 times, up to 1,000 times per level, but each individual run must not exceed a sort of certain amount of computation, which is higher than what people would tend to hit on the whole if you write your kernel as to avoid things like arbitrary large like loops and stuff. Because the kernel exits and RAM is cleared, the WebAssembly memory is cleared between runs, the kernel is given a durable file system, which is effectively a sort of tree-like key value store that allows the kernel to persist state between runs. You have to wait 2 weeks from a commitment being posted until that commitment is cemented to allow other people to potentially refute it. What you don't want to do is have a dishonest operator post a invalid commitment on layer 1, and that to automatically be trusted. Because if a dishonest committer can get a sort of arbitrary world hash sort of confirmed, cemented on layer 1, then nobody else can follow and be honest, because they don't know the exact state that the operator has, and that exact state could be, I get all the funds on layer 2 for this particular rollup. So that's why you have to wait the 2 weeks to effectively allow the one or more honest operators on that rollup to refute any dishonest ones.